In this video, we're going to discuss partial pressures of gases. So what is a partial pressure? When I think of a container and it has some gas, those gases are bouncing against the walls. They're hitting it, they're exerting some amount of pressure. Well, each particle is doing this. Each particle hits the walls and exerts some pressure. And so if I just have those two particles, the pressure total is the sum of the pressure of the first particle plus the pressure of the second particle. Think about our pressure and moles relation. If I just have less moles, I have less pressure. Remember, if your moles go down, your pressure goes down. This is because our pressure is the sum of all of the impacts. Well, that doesn't care what the gas is. If I have two different gases and they're bouncing around, they're still impacting. There's no reason pressure 2 has to be a separate particle of the same gas. Pressure 2 could just be a different species of gas. Whatever mixture you have of gases, whether that's 100% one type of gas or a mix of 2/3 and 1/3, or a mix where you have very little of one, several of another, and a whole bunch of a third one, your pressure is always just equal to the sum of the individual particles' pressures hitting those containers. Now, normally we don't talk about the individual particles, we talk about the whole collection. When we do pressure, it's normally versus moles. We have a pressure volume equals nRT. Assuming our temperature and our volume aren't allowed to change, we really have pressure 1 moles 1 equals pressure 2 moles 2. Our pressure is just directly tied to the moles of gas. It doesn't matter which gas it is if you have a mixture. Half those particles exert half the pressure. A third of those particles exert 1/3 of the pressure. So if we were to go think about some of these containers, well, our pressure total, 1/3 of that is the white spot ones, and 2/3 of that are the green spot ones. The sum of those two will add up to the pressure total in that container. Our pressure is always just the sum of all the particles. Now, it's hard to count the moles of gas, but often we can figure out how much of each individual gas we add. We add the first one, we see what pressure gives us. We add the second one, we see what pressure goes up to. If you had a tank that was empty, and so the pressure dial read 0, and then you went and you put a little bit of gas in it, your pressure dial goes up to 1 atmosphere. Well, then the pressure of the white dots is 1 atmosphere. If I then go and add some more dots, the dial goes up further, and we get up to 2.5 atmospheres. Well, that 2.5 is the total. So my 2.5 is going to equal the white dots plus the green dots, whatever that species of gas is. We knew from our original adding that, well, 1 atmosphere was from the white dots. So I can subtract that from both sides. Minus 1 atmosphere, minus 1 atmosphere. The additional 1.5 atmospheres that the dial went up is our green gas. We can literally just sum the two pressures together to get our total. If the total is 2.5, and we know 1 atmosphere of it came from the first gas, the remaining 1.5 must have come from the second gas. This is the idea of Dalton's partial pressures, which was just that it didn't matter that they were different gases. If you'd had one container and you put in one particle of, say, dihydrogen, and it gave you 1 atmosphere, and then you put in a second particle and it doubled to 2 atmospheres, and you put in a third particle and it went up to 3 atmospheres. Being the same gas, Well, yeah, 3 times the amount of stuff, I should have 3 times the force. It wasn't as obvious that different gases would behave the same, but they do. If my first dot goes in and gives me 1 atmosphere, and then my second dot is a different gas, and it goes in, well, the total is now just 2 atmospheres. Add a third dot, my total is now just 3 atmospheres. 3 times the stuff is 3 times the pressure. Well, how do we determine the pressures then, and how does this help us understand things like mixtures of gases? For that, we need mole fraction. Symbol X of whatever the gas. X of N2, X of dihydrogen, X of CO2. Mole fraction just tells us what percent of the moles are that gas. If I have 100 moles of just gas, but I know that the mole fraction of N2 is 80%. But I know that the mole fraction of N2 is 80%, which we do as a decimal, so 0.80. Well, this tells us that out of those 100 moles, well, 80 of the moles are N2. The other 20 are something else. On Earth, dioxygen. Well, this means in a container, I've got plenty of N2 floating around, and I have a little bit of the other gas. Of all the pressure being applied, 8 out of every 10 hits comes from dinitrogen, and 2 out of every 10 hits comes from the other gas. This just means that 80% of the impacts come from dinitrogen, because it is 80% of the particles. We can find the pressure of the dinitrogen. The pressure of your gas is always equal to the pressure total times the mole fraction of that gas. The reason, just 80% of the particles make 80% of the impacts, which makes 80% of the force. We can always find what pressure that individual gas is exerting inside our container. This means that your pressure total is always going to be equal to pressure total times the mole fraction of compound A plus pressure total times the mole fraction of compound B, and so on and so on and so on through all of your possible gases. They all have to add up to the total. The sum of all your mole fractions has to equal 1. They have to equal up to all the particles. Well, this makes it a little bit handy for determining what the other gas amounts are. If you can determine what fraction of a gas pressure came from one gas, you can figure out how much the mixture was. Example, I have a flask, seal it up, and there is some gases, but we're not sure of the mixture. We know that this is 1 liter, and it starts at 1 atmosphere. We'll say it's at freezing, 273 Kelvin. Makes our calculations easy. If we calculate out the moles for that gas, what we'll find is that the moles in our container must be 0.044614 mole of gases, of all the gases. Well, there's chemicals that can remove dioxygen. So if we know the mixture has some amount of N2, some amount of O2, but we don't know how much of each, you can put in a chemical whose job is that it scrubs oxygen. It just sits here, and anytime the oxygen dots run into it, they go away. As a result, your pressure goes down. What we find afterwards is that we're still 1 liter. We're still 273 Kelvin, but our pressure has dropped to 0.0783 atmospheres. We've lost pressure. The oxygen got consumed by this scrubbing agent. What this tells us is that originally our pressure total was 1 atmosphere. Well, the remaining pressure must be anything that wasn't oxygen, so this is our N2. My pressure total is going to equal my pressure of N2 plus my pressure of O2. The pressure we lost was the O2's pressure. So I just have to subtract them. 1.0 minus 0.783 is going to equal pressure of O2. We can find that in that container there had been 0.217 atmospheres of dioxygen. By determining the pressures of N2 and O2, well, we can find their mole fraction. I know that the pressure of N2 must equal the pressure total times the mole fraction of N2. Because we determined after scrubbing all the oxygen that there was 0.783 atmospheres of N2, and there had been 1.0 atmospheres total, I can solve for the mole fraction of N2. I can actually figure out what percentage of the particles were dinitrogen. Divide it across, what we'll find is that it's, because we started with 1 atmosphere, it makes calculation easy, but it's 0.783 is the mole fraction of N2. 0.783 divided by 1, the atmospheres cancel and we just get our fraction decimal. If we'd used a starting pressure that wasn't 1, the math would have been slightly different. But nonetheless, what we find is that it was 78.3% dinitrogen. If we do the same thing for pressure of oxygen, we'll end up dividing by 1 again. What we can find is that the mole fraction of dioxygen was 0.217. It was 21.7% dioxygen. For having a mixture of gas, how do you determine what is in it? Partial pressures can be a very helpful tool for identifying the mix and makeup you have for that gas. Basic takeaways from partial pressure. Your pressure total is always going to be the pressure of the individual gases, and the pressure of the individual gas is always equal to the pressure total times the mole fraction. It just comes down to the number. Every species of gas is considered to exert the same pressure for the same number. If one of them has higher number, it's going to exert more of the pressure, but the container just sums all the pressure up. The walls of that container get hit by all the gas. It doesn't care which gas is hitting it, it's still taking an impact.